All right, this is section 2.8, function operations and composition of functions, and also difference quotient. Um, Sorry, if you notice, I've already worked out some of the examples here. This is my second recording of this video. It's just the first time I recorded it without audio. So that's okay. We'll just go through it. So let's begin with function operations. So right now we're dealing with sums, differences, products, and quotients of functions. All right, so if f and g are two given functions and x is in the domain of each one of them, then we have a new function called f plus g, which is just made up of f plus g, f minus g of x, which is f of x minus g of x, f times g of x, which is f of x times g of x, and the quotient f divided by g of x, which is f of x divided by g of x. Just be careful not to divide by 0. Okay, so let's get into these examples. Sorry, I already worked them out. Again, this is just because I'm recording this video again, now this time with audio. So if you're given the function 3x minus 4, that's f of x, and you're given the function g of x 2x, compute this new function f plus g. And well, the sum is just f of x plus g of x, so 3x minus 4, that's my f function, plus the g function 2x. And once you collect like terms, that's 5x minus 4. What is f minus g of x? Well, it's f of x minus g of x. So that's 3x minus 4 minus 2x. Collecting like terms gives us x minus 4. F times g of x. Well, that's f of x times g of x. And it's 3x minus 4 times 2x. And if you multiply that out, that should give us 6x squared minus 8x. The quotient, f over g of x, f divided by g of x, well, it's just f of x divided by g of x. And in our particular scenario, that just means 3x minus 4 divided by 2x. Just be careful here, the domain of this new function is everything except for 0. All real numbers except for 0. Why? Because we do not want to divide by 0 down here. And 0 is the only value that makes the denominator 0. Alright, so next example, something similar. You're given two functions, f of x and g of x. And now what you want to do is the same thing. Let's first begin by doing f plus g of x. So f of x plus g of x. And then I just rewrote it so that it looks like it's in descending order. F minus g of x is something similar. Just I now have some negatives. So 5x minus 4 minus x squared. The product f times g of x is just 5x minus 4 times x squared. And if you multiply that out, you should end up with 5x cubed minus 4x squared. F divided by g of x is just 5x minus 4 divided by x squared. And here, the domain of this function, again, I do not want to divide by 0. So what makes this denominator 0? Well, I think the only value that makes the denominator 0 is 0 itself. So it's everything, all real numbers except for 0. All right. So hopefully that is relatively straightforward. These operations with functions. Just make sure that whenever you're dealing with division, you pay attention to the denominator. All right, difference quotients. So difference quotient, what it is the slope of a secant line. Yeah, so a straight line, so if you're dealing with a straight line and you grab any 2 points on a straight line, it has a slope, and if you pick another pair of points on a straight line, the slope is the same. The slope is constant no matter what 2 points you choose on a straight line. But if you're dealing with a curve, if you pick 2 points on a curve and you draw a line through those 2 points, you might have different slopes through points. So if you look at my picture here, I drew I have this little curve in black. That's my function f of x. And imagine I pick 2 points on that curve. I have this point right here, which has coordinates x, comma f of x. I wrote them up here, over here on the left-hand side, x, comma f of x. That's a point on my curve. And now imagine I have another point on my curve. I'm calling it x plus h. So from x, I went h units a little bit further down the line to the right, and now I have a new point called x plus h. And well, if I plug in x plus h into my function, I get a y value called f of x plus h. So I have 2 points on my graph. One of them has coordinates x, comma f of x. So x, f of x, that's up here. I know that that's kind of ugly. And the other one is x plus h, comma f of x plus h. So x plus h, comma f of x plus h. And right now what I'm interested in is the line that joins these 2 points. This line is called a secant line. Yeah, so this is a secant line, and right now what I want to do is find the slope of this secant line. Well, we know how to find slope. A couple of videos earlier we were playing with slope, and so I have 2 points, and I want to find the slope of this secant line. And well, the slope is it's up here. It's this y, f of x plus h, minus f of x divided by x plus h minus x. And if you see this, so in this denominator down here, what ends up happening is that the x plus h minus x, well, the x's cancel out, and all you end up with is just h in the denominator. And this is the slope of a secant line. Yeah, think about it as that. It's just slope of a secant line. Later on in Calc 1, you're going to be putting this together with limits to find derivatives. So if you feel comfortable and confident about forming and simplifying difference quotients right now, then you're on a good trajectory for Calc 1. All right, so let's look at some examples here. Again, I apologize, all of these things are already worked out. I wanted to work them out with you, but I recorded this video earlier without any sound, so I'm just going over it again. So let's form the difference quotient for this function, 4x minus 6. So what I'm going to begin by doing is, well, I need to form the difference quotient. So f of x plus h minus f of x divided by h. If you think about it, so the difference quotient is made up of 3 little elements. There's the f of x plus h part, there's the f of x part, and then there's the h down here. The f of x and the h are super easy. Those are gimmies. Those were given to you. The h is really nothing. It's just a variable h. F of x is just a function that you were already given. So minus my function. The only thing that maybe has some complication is the f of x plus h. What does that mean? Well, f of x plus h, what it means is replace all of your x's in your function with x plus h. So I'm looking at my function up here. All of the x's, I'm going to replace them with x plus h. And that's why I have what I have written here. I have 4, and then I open a parentheses. I change my x to x plus h. That's why I have a parentheses. Minus 6, minus, and then I put a parentheses here, because this minus is going to affect my whole function f of x. That's it. This is the difference quotient right there. The instructions just say to find the difference quotient. So we have found it. That's it. I have found the difference quotient. The difficulty becomes simplifying the difference quotient. So let me simplify this difference quotient as much as I can. So in order to do that, I'm going to distribute this 4. So 4 is going to multiply x, and 4 is going to multiply h. I'm going to distribute this -1. So this -1 is going to be applied here. So that looks like this. 4x plus 4h minus 6 minus 4x plus 6. This plus happens because this negative times this negative becomes positive. And now, you should notice, if you do this correctly, a lot of terms usually cancel out. Usually, you should just end up with things that just have h. So this 4x minus 4x, those are gone. 6 minus 6 is gone. And so then all I end up with, once everything cancels out, is just 4h divided by h. And while the h's, since I'm doing division here, also cancel, and 4. 4 is the most simplified form of my difference quotient for this function. In Calc 1, what you'll discover is that the derivative of this function f of x is just 4, whatever that means right now. All right, so hopefully you agree with my steps in there, and let me move on to the next example. All right, so again, same thing. I gotta find the difference quotient for the function 2x squared minus x. All right, so I have written the difference quotient up here. This is just the general thing. Again, remember, f of x is given to you, h is given to you, so that should be straightforward. So I have h down here minus, I put my whole function f of x inside a parentheses because I have to distribute that negative. So be careful with that. Be careful with the signs. I always put a parenthesis around my function there. And now I gotta form, what is f of x plus h? F of x plus h is, well, let me go look back at my function. I'm gonna have to replace all of the x's with x plus h. And that's what I've done right here. So I have 2 times x plus h squared. I put a parenthesis around the x plus h part because it's being squared, minus, and then originally I had just x, but now it's x plus h. So I hope that we agree on the forming of the difference quotient. This is the correct difference quotient that we should have. And technically that's it. I'm done. I have formed the difference quotient. That is the difference quotient right there. But now what I'm going to try to do is simplify it. So to simplify this difference quotient, what I'm going to do is first I'm going to multiply x plus h squared. I'm actually going to expand that. Just FOIL it. And then I'm going to distribute this 2 into that. I'm going to distribute this negative, and I'm going to distribute this negative. Yeah, so those are the things I got to do. That's my next step. So if I do that all correctly, I should end up with 2x squared plus 4xh plus 2h squared minus x minus h minus 2x squared plus x. Hopefully we agree on that. That's what happens if I distribute negatives and multiply a 2 and square things. That's what I should end up with. And again, you know that you're in the right track to simplifying this difference quotient if a lot of things cancel. So for instance, right now, this 2x squared minus 2x squared, those are going to be gone. Negative x plus x, well, that's 0. Okay, so the things that only have x should cancel out. So terms with only x's should cancel out. And so then what I end up with is 4xh plus 2h squared minus h, all of that divided by h. And then finally, in this numerator, I can factor out an h from everything. If you think about it, there are 3 terms in my numerator. Each one involves h. So I should be able to factor out an h from everything. And then that h that I factor out cancels with the h in the denominator. And once that happens, I end up with 4x plus 2h minus 1. That is the most simplified form of my difference quotient. Crazy to think that this 4x plus 2h minus 1 is equivalent to this messy fraction up here. But it is. Alright, so hopefully we agree on our solution here to this difference quotient. If not, check your work. Alright, so the last example of forming this difference quotient. So originally, I think you had some similar function here, x squared something something. Let's change that. Let's change it. Let's change it to 1 over x. Let's find the difference quotient for 1 over x. That's a little bit more challenging. So, I don't know. Let's see. I'm sure we can do it. I'm positive in our ability. So let's try to first form the difference quotient. Also, if you want to, you should stop the video and try to kind of do it on your own, and then just look at the end result and see if we agree. So f of x plus h in this case, f of x plus h is, let me replace my x's with x plus h. So that's 1 divided by x plus h minus the original function and all of that over h. So that's it. That is the difference quotient right there. I guess I'm done. It's the simplifying part that gets difficult. So let me look at the numerator. Here, there's this numerator. The numerator involves a subtraction of fractions. I need to subtract fractions. In order to subtract fractions, I need to get a common denominator. And while I'm looking at this denominator of this fraction, it's x plus h. I'm looking at the denominator of the other fraction, is just x. What would be a good common denominator for these two fractions? And hopefully we agree that it's just the product of the two denominators. All right, so my common denominator should be x times x plus h. So then that means that this fraction on the left, I'm going to multiply by x in the numerator and x in the denominator. This fraction on the right, I'm going to multiply by x plus h in the denominator and x plus h in the numerator. And once I do that and combine my fractions into a single one, I actually do the subtraction, then I should end up with this fraction right here. X minus, I was careful to put a parenthesis here, x minus x plus h divided by x times x plus h, and all of that divided by h. So I hope that we agree on this step right here. All right, next thing. So the next thing is, now let me simplify this fraction on the numerator again a little bit. I'm going to distribute this negative. If I distribute this negative, I'm going to have x minus x and then minus h as well. And the x minus x, well, that becomes 0. So I should just end up with negative h divided by x times x plus h, and all of that over h. All right, now how do I make sense of this ugly compound fraction? Well, think about it. It just means the top fraction, negative h over x times x plus h divided by h. Well, that's the same thing as saying the top fraction times the reciprocal of this denominator. So it's the top fraction times the reciprocal of my denominator, 1 over h. And then what ends up happening there is that the h up here in this numerator, this h in this denominator cancel, and I think I am at the simplified form of the difference quotient here. The simplified form is just negative 1 divided by x times x plus h. This one's a little bit more challenging, but with a little bit of care and perseverance, we should be good. All right, let's move on. Let's talk about composition of functions. All right, so we are plugging in a function into another one. There is a little argument here about a function called w of x, which is supposed to be your washing machine function. There's another function called the d of x, the dryer function, and you're plugging in the washing machine into the dryer machine function, etc., etc. Let me just, something similar here. Let me just be a little bit more general. So this is the type of notation that you will see. The way you say this is f of g of x, f of g of x. And what you're supposed to do is you're supposed to plug in the right function into the left one. So f of g of x. You plugged in the right function into the left one. There could be composition of 3 functions. You could have h of f of g. And what you have to do is plug in the right one into the rightmost, to the middle to the left. So it's always going from right to left. So f of g of x, the way this function works is, well, my input x first has to go through first function, g. So my input has to first go through g. So x comes from the domain of g. G does something to it, and it spits out what's called g of x. So g of x lives in the range of g, which turns out is also the domain of this other function called f. F picks up this output for g and does something to it called, and then gives you what's now called f of g of x, and now this is in the range of f. So it's just linking functions together from right to left. All right, so let's do some composition of functions here. So for these examples, what you want to do is find f of g of x and g of f of x, and also find the domain of each composition. You gotta find the domain of the composition. And finding the domain of composition of functions can be sort of tricky. So I put some little guidelines over here to kind of help you figure out what is the domain of a composition. So suppose I wanted to find the domain of f of g of x. In order to do that, I have to first find the domain of both g and f. So that's part 1 and part 2. I gotta find the domain of g of x, and I gotta find the domain of f of x. Remember how this composition works. X has to first get through g. So we need to respect the domain of g. Because if my input cannot even go through g, then it cannot continue going forward in this composition of functions. So the domain of the inner function is definitely important. So you need to know the domain of g, you need to know the domain of the outer function too. And then here in step 3, what I've said is find all of the x's that make g of x be not, or not be, I should have said, not be in the domain of f. So think about, yeah, this is kind of a weird situation here. So you gotta find values of x that make g of x be not in the domain of f. And then turns out that the domain of the composition, the domain of f of g of x, is going to be equal to the domain of g of x, so the domain of the inner function, minus whatever values of x you found from step 3. All right, let's see if we can make this work. So let's think about an example here. So I have two functions. I have the function 3x minus 4, that's f of x. F of x is 3x minus 4. Its domain is from negative infinity to positive infinity, because that's just a line. And then I have another function g of x, which is the square root of x minus 1. Its domain is from 1 to positive infinity. I hope that you agree on these domains of my original functions. I need them. All right, I gotta compute f of g of x. All right, so I gotta plug in the function g into f. All right, so I'm looking at my function f right here, and into it I gotta change all of the x's to g of x. So that's what this line is saying. I change my x right there to g of x. And then I'll actually write out what g of x is. Well, g of x is the square root of x minus 1. And then this is just multiplication, so that's it. That is f of g of x right there. I have plugged in the function g into my function f. And this is the result. This is the simplified form of that. Now, what's the domain of this function? So remember, in order to find the domain, we definitely need to respect the domain of the inner function g of x. What's the domain of the inner function g of x? We said it was 1 to positive infinity. Now, we also need to identify any possible x's that make g of x not be in the domain of f of x. So we need to find any x's that make g of x be outside of the domain of f of x. Well, the domain of f of x is everything, so there are no such x's. And so then I'm going to conclude that the domain of this composition is just the domain of g of x, 1 to infinity. So I hope we agree on that. All right, let's do the second part of this exercise. We gotta do g of f of x. So now I am plugging f into g. So I'm looking at the function g now. Anywhere where I have x's, I'm gonna replace them with f of x. All right, well then that's the square root of f of x minus 1. Let me change out f of x to what it's supposed to be. It's supposed to be 3x minus 4 minus 1. And well, that becomes the square root of 3x minus 5. All right, so what's the domain of this thing? What's the domain? So if I gotta respect the domain of the inner function. I gotta respect the domain of the inner function. The domain of the inner function is negative infinity to positive infinity. All right, and now I gotta identify any values of f of x that make any values of f of x. So I gotta find values of f of x that could potentially be outside of the domain of g of x. Yeah. So literally here, one thing I could possibly do here is set my function f of x, so 3x minus 4, equal to 1. Why 1? Because 1 was kind of the cutoff point for the domain of g of x. I mean, another way to see this is that, I mean, this is the simplified form of the composition. We do not want negatives inside the square root. So let's just figure out what's going to make it negative. So I'm going to set the inside of my square root equal to 0. That gives me 5/3. And turns out that is things that are bigger than 5/3. That should be the domain of this composition of functions. These rules over here for finding the domain of a composition still apply. It's just that these particular functions that we're working with do not lend themselves kind of nicely to using these rules. But, I mean, in this particular case, we were able to just pretty much look at the resulting function and think, well, what would be the domain of that? Well, we don't want negatives inside the radical, so figure out what makes the inside of the radical negative. All right, so my domain, yeah, is from 5/3 to positive infinity. This next example, I'll leave it up to you to work it out. I'm going to move on to the next one because I think the next one is more interesting. All right, so let me compute f of g of x. I am plugging in g into f. All right, so I'm looking at f. Anywhere where I have x's, I'm going to replace them with g. So that x right there, so this is the square root of 3x plus 1 minus 2. 1 minus 2 is negative 1. All right, so what's I think that is it. That is my composition right there. Let me kind of space it out here. So that is my composition. That is the simplified form, and I am going to go ahead and say that the domain of this new function is 1/3 to positive infinity. I hope that you agree with that domain. All right, so let's see. Let me also separate this out here. So let me do g of f of x. So I am plugging f into g now. So that's going to be 3 times the square root of x minus 2 plus 1. And while the domain of this function is just the domain of f of x originally. It's from 2 to infinity. Again, I hope that we agree on this. And then this last little part here, g composed of g of x. So I gotta plug in g into g. So I'm looking at g right there. Anywhere where I have x's at g, I'm gonna change the x's to g of x. So that's 3 times 3x plus 1, and all of that plus 1. Distribute this 3, collect like terms, and I end up with this function 9x plus 4. And I would say that the domain of that is everything from negative infinity to positive infinity. All right, so be careful with the domain of composition of functions. These little steps for finding the domain are true. It just depends on also depends on the functions that you're dealing with. Sometimes it's you definitely need to think about the steps. Other times it's a little bit more straightforward. Last thing in this section: decomposition of functions, decomposing a function. So in Calc 1 or in Calc 2 as well, it might be advantageous to you to sometimes think about functions as composition of functions, as one function being inside another one, so that you can make a substitution and make your life a little bit easier when it comes to finding integrals or derivatives or whatnot. So it's useful to be able to decompose functions. So let's think about this first function, f of x. I want to be able to break it up as I want to think about it as a function inside another function. So I got to think about these functions. So I'm going to come up with two new functions. One of them is called h of x, the other one is g of x. And I'm saying that h of x is equal to 3x minus 1, g of x is equal to x to the fourth. And what I claim is that the function f of x is equal to g of h of x. I hope that you agree. I am plugging h into g. So I am plugging 3x minus 1 into x to the fourth, and I get what I started with. I hope that makes sense. Let's think about the next one. You have a function g of x, which is the cubic root of x squared plus 2. Again, I kind of want to break this function up and think about it as a function inside another one. So I would say that the outer function should be the cubic root. The inner function should be x squared plus 2. And well, yeah, that is what it is. I call the outer function f of x. I call the inner function h of x. So it's f of h of x. That's my original. All right. So think about this other weird function. Well, this is not a weird function. We're very used to this parabola, x squared. Can you decompose it? Can you think of x squared as a function inside another one? Well, what I claim here is that I can think of two functions. One of them is just x, and the other one is the function itself, x squared. And I could plug in f into g and get what I started with, or I could plug in g into f and also get what I started with. I hope that you agree with that, because it's true. So yeah, sometimes decomposing functions is kind of trivial. It just comes down to the identity function x and the function itself. All right, so again, sorry that I didn't give you a chance to work out these examples. This is the second recording of this video. Now hopefully it has audio. And thank you. I'll see you in the next video.